Hello everyone, welcome back to Introduction to Semiconductor Devices. So in the last lecture, we understood the last few lectures, we have understood the MOS capacitor electrostatics, and we also looked at the various non-idealities. So today the agenda is to understand the CV of a MOSFET, MOS capacitor, sorry. A CV is a very, very important measurement technique which will help us analyze the behavior of a MOS structure. Okay. So we will spend some time today on that. So we have seen this already. So wherein you have the MOS structure, metal, oxide, and semiconductor. We have analyzed this in detail. So essentially what we have been doing is we are drawing a band diagram and all in this direction basically. You're going from metal to oxide to semiconductor. What was happening? We understood that in multiple ways. So today, we would like to understand CV. When you take off a CV, capacitor, right? If you take a parallel plate capacitor, what is its capacitance? The capacitance is simply, the capacity to store charge. Let's say you apply a positive voltage, apply a charge, voltage to one of the plates. Then it develops a positive charge, and there will be an equal and opposite negative charge on the other plate. And there is a certain amount of energy stored in the capacitor. The ratio of charge to voltage is your capacitance, right? So for a simple parallel plate capacitor, if you add a plus delta Q, there will be automatically a minus delta Q on the other plate, and it's a constant. The capacitance is constant. But in semiconductor devices, the capacitance is not constant. We have seen one example in the case of the PN junction diode in reverse bias. So as you increase the reverse bias, we saw that the depletion width was increasing and the capacitance was changing, right? So now we would like to understand what happens to the MOS device. So it's not a simple PN junction, but you have an oxide in between, and then the metal and a semiconductor. To understand that, what we will do is we'll apply two voltages to the MOS structure. Okay. One is a DC voltage, which I am calling as VG, right? This is basically a biasing voltage. So I'll change this from accumulation to depletion to inversion. I'll sweep through these regimes. So I'm essentially changing the DC bias when I change my VG. In addition to that, I'll apply a AC signal. Okay. So the total AC signal is basically VG plus some AC signal, wherein this AC Vs is a small signal voltage. It can be something like 25 to 50 millivolts. It's a small signal. It's not going to perturb the DC operating point of the MOS capacitor. And then I'll have another frequency that could be anywhere, it could be 1 hertz to even 1 megahertz. It could be a wide range of frequencies. Okay. So I'm doing I'm checking the response for small signal, right? This omega, the Vs is small signal voltage. Now, how does this structure respond, right? But how do you measure capacitance, right? If you want to measure capacitance, what we will do is we'll essentially change, right? We will C is basically dq by dV. So I'll change my AC signal. So that is my frequency, certain frequency. I'm changing that. I'm looking at the response of the charge, and then from that I'm calculating the capacitance. In practice, the way to do this would be I'll apply a voltage with respect to time. So let's say I have I'll sort of step voltage I'll apply. So basically I have my V1, V2, V3 and V4. So I'm stepping my DC voltage. Okay. This time duration could be like 1 second. It's a lot of time. It could be millisecond as well. So as a function of time, I'm changing my DC voltage. So this is my VG. Sorry, VG is changing in this direction. Okay. As I step my voltage, in addition to DC, I have a small AC signal on this, riding on this, right? On this, there is a small AC signal like this. So I'll use an LCR meter. That's a standard equipment to measure the capacitance. So I'll use an LCR meter and I'll measure C1 here, C2 here, C3 here, and C4 here. So I'm getting capacitance as a function of voltage. So I'll take this and I'll plot voltage versus capacitance. So that's what we call as a CV. It could be some shape like this. So it's essentially a collection of these points, I'll have some V1, C1, V4, C4. So a collection of these points is essentially a CV curve. And that gives you a whole lot of information. What sort of information? Well, to understand that, let's go back to what the capacitance will give you. Okay. So capacitance is simply dq by dv, right? What is this Q? Well, this is going to be charge on the gate and gate voltage. That's what we are using the bulk as a reference, substrate as a reference, we're grounding it. We have already seen what is Vg. Vg was, there's a relation between gate oxide and the surface potential, which is the voltage across a semiconductor, right? So that was minus Qd divided by Cox plus phi s, which is surface potential, right? So if I take a derivative here, dVg by dQg, I'll take. Well, Qd is actually, this is minus, this is going to be Qg. I mean, depletion charge is simply going to be inverse of the gate charge, right? Okay, this is valid only in the depletion region, by the way. Not valid in depletion regime. Because in accumulation and inversion, we saw that, more or less the surface potential remains constant. Okay? It's a slightly different thing. Okay. So when you have this, what should happen? So this will be simply 1 over Cox plus d phi s divided by dVg. And the second thing is essentially telling you the, sorry, dQg, not phi s. This is not Vg, but this is dQg. How is the charge varying with respect to the potential, right? So this second term is equal to 1 over C depletion. Okay. So overall, 1 over C, basically the gate capacitance, is equal to 1 over C oxide capacitance plus the depletion capacitance. So in effect, what we are seeing is you have a oxide capacitance and then you have a depletion capacitance in series. So that seems reasonable, right? We saw that there's a depletion region created. So just under the oxide, there's going to be a depletion capacitance. And then there is a series relation with the gate oxide capacitance. Okay. So you have these two capacitances. So this relation this helps in understanding the behavior of carriers in accumulation, depletion, and inversion. Okay, so we study this function, right, how this is happening. So that is the analysis, CV analysis. So how does the CV curve look like? We'll first show you that and we'll explain how that is coming about. So the CV curve looks like this. Okay, so you have basically on the y-axis C by Cox. So I'm plotting the capacitance versus Cox, and then x-axis is the voltage. Okay. So we will understand this in by region. So first let's consider the accumulation region, and this is a p-type substrate. Okay. So p-type substrate. Let's assume that for a moment. Just excuse me for a moment. All right. So how does it look like? What happens in accumulation? If you take a p-type substrate and apply negative voltage to it, you're essentially going to drive the holes. You're going to attract the holes to the interface, and because of that, you have accumulation, right? So that is schematically shown here. So this is your hole accumulation. So this happens right at the interface. And there's an opposite, there's going to be a minus Q here and there's going to be a plus Q here. It's always, going to be valid for any capacitor structure. So the voltages below zero, like if I call this 0 here, for example, this is my accumulation. And in accumulation, what you're seeing is, if I, this plus Q and minus Q are caused by the DC voltage, right? VG. I'm biasing the capacitor, and the small signal is going to cause a small, minus Q, minus delta Q, let's say. This is a small signal contribution, this black region, right? So if we have this minus Q here, the minus delta Q, there's going to be a plus delta Q. So you change the gate voltage by a tiny amount. The balancing voltage, you change the gate charge by a tiny amount, and then the balancing charge will be in the accumulation charge, in the accumulation. So basically your ACC charge increases in response to small signal. The small signal is not really changing the bias, biasing condition. It's still accumulation. But for every small delta Q that we add on the gate, there will be a positive delta Q that will be added on the accumulation layer. So the capacitance, it's like a parallel plate capacitor. You add a plus delta Q on the one plate, minus delta Q will be on the other plate. So the capacitance is going to be C accumulation, let's call it. It's going to be C ox divided by, sorry, not C ox, I'm sorry, it should be epsilon oxide divided by T of the oxide, thickness of the oxide. Okay. Well, this is the overall capacitance, right? So even I could call it, in the accumulation, I can write it as, I can remove this part. I can say C is equal to this in accumulation. So in understanding the CV, we have to think about, for every plus delta Q, where is the minus delta Q going to come from? The balancing charge, where is it going to come from? That will determine your capacitance. Okay. And remember, this is basically in the accumulation, it's a purely geometric effect, geometric capacitance, you can say. Okay. What happens in depletion? So we know that as you increase the gate voltage from 0 onwards, it will be depletion. Right? This will be depletion. Right? What happens? So we're going to push away the holes. This is a P-type substrate, so we're going to push away the holes. So you get exposed acceptors. Exposed Na minus also. Exposed Na minus. Exposed acceptors. So that is going to balance. So basically this balanced charges. So the electrons on the metal has positive charge now, and that will be balanced by the negative charge created by the depletion region. Now if you add a tiny delta Q on the metal, the minus delta Q is going to come from the edge of the depletion region. Remember, we are not changing the bias, so it's a small change. So this is the balancing delta Q in depletion region. So basically, W is going to change from W to W plus delta W, something small change in the depletion width. Okay, so that will lead to a capacitance. So when you go from ACC, accumulation to depletion, small depletion width, or I should say small change in depletion width. Okay. So this gives you what is known as depletion capacitance C depletion, which is simply epsilon by the thickness of the depletion width, thickness of the depletion region. So this we have discussed when we talked about PN junctions in reverse bias, right? So even though it is very different from what parallel plate capacitor. You have parallel plate capacitor where plus Q and minus Q, right? Separated by insulator. But in the case of a semiconductor depletion region, it's a distributed charge. Na is not like plus Q minus Q. It's a distributed charge. But we saw that overall, even then, the net capacitance is simply going to be epsilon by width of the depletion region. Okay. So what happens? Well, As W depletion increases, C depletion reduces. Okay, that's what we expect in a year. Depletion capacitance is reducing. One thing to note in this business is that okay, I can't draw a straight line. Okay, so it becomes a sort of a challenge. Yeah. So in both accumulation and depletion, majority carrier response is needed. In accumulation, it's simply the majority carriers, which are holes in this case, are going to accumulate. In the depletion, we're going to push away the majority carriers. So it is still the majority carrier response. Okay, and it turns out that majority carrier response time is approximately 1 to 100 picoseconds. It's very fast compared to the applied frequencies. Okay, very fast compared to applied frequencies. Okay, so that's why we don't really have much of a okay. We will discuss that. Okay, majority carrier response. So let's, before I talk about that, let me talk about how the CV changes. Okay, so in accumulation we saw that it's purely geometric capacitance and this Cox. So when we plot C by Cox, it's going to be 1. Okay, in accumulation. When we go to depletion, C effective, right? C effective, or whatever C you want to call it, C. Let's just call it C. Right? C is simply C depletion times Cox divided by C depletion plus Cox. Because we have two capacitors in series right here, Cox and C depletion. Right? You have to write this. And your C depletion is reducing, right? When Vg increases, W increases, so C depletion decreases, therefore C decreases. Okay. So that's why as you go into depletion, there's a gradual change in the capacitance. The capacitance falls. Now, what is the minimum value? Well, the minimum C min. So minimum value of capacitance you will get when you get the maximum depletion width, right? So C min equal to C depletion at W equal to W max. Whatever is the maximum depletion width? W max occurs when phi s equal to phi f. You have the maximum depletion width, and with respect to, if you calculate the C depletion at that point, you will get the C minimum. Okay. So why does the majority carrier response time play a role here? We said majority carrier response time is very fast compared to the applied frequencies. So in CV, we tend to make measurements at quite different frequencies. One of them we call as low frequency, one of them we call as high frequency. So remember, we talked about an AC component, AC signal, small signal, which has an omega term, which is a frequency term. Okay. So if this frequency term is anywhere from 1 hertz to up to 1 megahertz, we call it HFCV. Okay. If you go below that, what happens is we call this as LFCV. Omega less than 1 hertz, I would say. In fact, millihertz kind of range we do. We do what is called as quasi-static measurement to actually capture LFCV. Okay. Experimentally, it's quite challenging to measure LFCV. HFCV is quite easy. Okay. So you see that since majority carrier response time is fast, it's in the order of picoseconds, you do measurements at whatever frequencies you want, but you're going to get CV which is identical. So the red curve is a HFCV, the black curve is a LFCV. In the accumulation and the depletion part, it is identical. Okay. This is ACC, and this is depletion to this point. So in ACC and depletion, the HFCV and LFCV are identical because majority carrier response time is much smaller than applied frequency. Okay, it is nearly identical, but one important difference exists. That is where the balancing charge happens. In accumulation, balancing charge is at AC inward interface, at the silicon dioxide interface. Whereas in depletion, there is nothing like, there is no the possibility of, inversion has not yet happened. Inversion requires a certain surface potential, right? We have not yet reached that. Till you reach it, you're going to simply push away the majority carriers. So balancing charge occurs at edge of depletion region. This is the primary difference between accumulation and depletion. Okay, physical locations are different, but you get, the time is still much faster compared to the applied frequencies. So of course that tells us that in inversion it's not going to be the same, right? Why is it not going to be the same? Well, in inversion charges are produced how? Are produced by EHP generation in depletion region, right? This is how inversion charges are produced. Well, yeah, correct, yeah. So what happens to these electron hole pairs which are produced? So what we need to do is, we look at how the electric field is, right? This is, let's say, X versus electric field, and you know that it's going to be like this. This is my depletion width, right? W. So a linear function, electric field is linear. So what will happen to holes? Holes will go this way and electrons will go in the opposite direction, right? This is how the charge separation happens. And because of that, if you are doing measurement at low frequency, what do I mean by low frequency? Well, my Vs sine omega t, right? It's very small, milliseconds, a millihertz kind of frequencies. Let's say omega tends to 0. It's very small frequency. That means I'm very gradually changing my Vg. Then you have a sufficient time for the minority carrier generation, or electron hole pair generation. Okay, so sufficient time for EHP generation. So what happens? They get generated and then they'll accumulate at the interface. Okay, inversion charge forms at the interface, right? So if you have the DC bias, okay, DC bias is such that you have this W here, which is depletion width, and effectively this will be W max. It will be the maximum depletion width possible in that, and then you add a plus delta Q here. So balancing charge at interface. The reason it's forming at interface is you are doing it very slowly. Remember, this is, I'm saying this is for LFCV and this is for HFCV. In LFCV, you're doing it very slowly in such a way that there is sufficient time for the electrons to accumulate, to come to the interface. So that forms the balancing charge. So your C is simply going to be Cox. And that is why, if you look at the curve here, LFCV curve, the black curve is LFCV and immediately goes up towards COX once inversion forms. So this point, I'll call it as VT, threshold voltage. So once you hit that, you have sufficient amount of inversion. And then whatever changes you do, it just happens at the interface and capacitance goes back up to COX. Okay. That's why C by COX is going to be 1. Whereas, if you do it at high frequency, HFCV, okay, let's say omega tends to infinity, okay. For our purposes, even megahertz is infinity, okay. So if you go to high frequency, your gate voltage is changing very, very fast. So inversion charge, or there is no sufficient time for EHP generation. So no inversion charge. I mean, there is a DC, whatever inversion, this is there still there. Okay, no, I should not write it, no inversion charge. Okay, that's not exactly correct. So I have my plus Q here, and my minus Q is formed by two of this. So this will be formed by Q depletion plus Q inversion. Both are minus. Both are exposed acceptors and in this case electrons, right? So you have these two charges. Now if I add a plus delta Q, the minus delta Q can only come from extending the depletion region. This is a balancing charge. Why this has to come at the edge of the depletion region? Because there is no sufficient time for electron hole pair generation. Okay. So the inversion charges cannot come to the interface. So, but we also know that once we reach threshold, there is a lot of screening because of the inversion charge. So the depletion width does not change so much. Okay. So W tends to be W max. So C depletion tends to be, or rather the total gate, right, gate capacitance, C is basically C depletion times C oxide divided by C depletion plus C oxide. So at maximum depletion width, C tends to be close to C depletion. We'll call it as C minimum. So that's why you see that there is this HFCV which does not go back up. It remains flat. So this is a primary difference between HFCV and LFCV. Okay. Please take your time and try to explain this by yourself, because this might seem simple, but this is quite subtle. In my case, the first time I learned this, I thought I understood it, but then after a couple of months, I realized when it was in the exam, I didn't understand anything. Okay, it's not a very easy thing. So it takes time. Please, take your time and understand all this. Okay. So fine, yeah, we get this C minimum. Okay. So by the shape of the CV, we can analyze a lot of things about the MOS device. We'll take some examples. We'll also run some nanohub simulations to show you how the parameters will affect CV. Okay. So so far we have considered only NMOS device, right? This was NMOS device. I didn't mention it, but this is a P-type substrate. All the charge diagrams are all for a P-type substrate. What happens if you take an N-type substrate? Okay. So to explain that, I have a exercise from the textbook. So please go and refer to exercise 16.4 in PRA. This is adapted from there. So essentially here the CV is shown on the top. So you see that there is a, if you have this is N substrate, right, PMOS. So when you apply a positive voltage, what happens? You'll accumulate electrons at the interface. So you have accumulation, and as you go and apply more and more negative voltages, you'll go into flat band, depletion, and then finally inversion, and like this. Okay, this is my LFCV. Okay, this is definitely LFCV. Okay, so we'll have to understand how each of these black points represents some kind of a physics, right? Accumulation, inversion, depletion, and so on. So we want to understand which point corresponds to which block charge, And in fact, you could also draw the band diagrams and look at, which accumulation, how does a band diagram look, and so on and so forth. You can do a lot more. We can give you a whole range of exercises. We'll give one of these such things in the assignment, and in the final exam, there's going to be something on this for sure. Okay. All right. So first, let us look at accumulation. Right. This is clearly accumulation. In accumulation, what do you expect? You have excess negative charge on the substrate. Okay. So, and that has to be at the interface, right? This is accumulation. So if you look at all these examples, this is accumulation of electrons. And this is holes on the metal, positive charge on the metal. Okay. So both these are right at the interfaces. So the condition G is accumulation, and the block charge is 3. So I'll write this answer as G3. So that will tell me what choice is correct. So I have to match all of these points to the block charges. Depletion, how does a depletion look like? Well, in depletion, there's no, you're pushing away electrons, so you'll have positive charge. And where do you have positive charge, which is balanced by a negative charge on the gate? So, well, okay, there's one more point that I have to discuss here, which is as you go from accumulation, right, as you keep decreasing the voltage, at one point you're getting to what is known as flat band. Flat band means with no applied voltage, there is, how do the bands look like? There are no bending of the bands, so there's no charges associated with applied gate voltage is 0. So this is my, this second picture is called as flat band. So I'll call this as F2. Okay. This is flat band condition without any applied voltage. When I apply a negative voltage, I'm depleting, and so depletion is going to be point E, and the corresponding charge diagram is going to be, we said depletion, we are uncovering the donors. So this is how, this is uncovered donors. So this is going to be E1, and D is basically the threshold, right? At the threshold at which you are the electron charge, or we are taking n-type substrate, so hole charge, inversion charge, right? Number of holes, P, right, is equal to Nd, donor charge in the substrate. See here, this is Nd, and this is the number of holes, so they're equal. So that's the onset of inversion, so threshold. So, okay, this is called as depletion to inversion transition, or VT, threshold. So this is going to be D phi. And the rest of them, right, A, B, C, semiconductor is already in inversion here. Okay. So when you have inversion, essentially you have plus Q and there's a large, minus Q and there's a large plus Q here. So all of these points are that. So I could write simply A4, B4, C4. So telling you that it's just inversion everywhere. All this, you can't distinguish from a qualitative picture. A, B, C, as A is going to have more inversion charge, but it's very difficult to distinguish that in a qualitative way in this sort of way, I think. So, but this sort of gives you the overall picture of how a CV looks like, right? So please take your time, review this video one more time and see how you can understand. So as I've been saying, it's a very, very useful thing. So practice band diagrams, practice block charge diagrams. So that will give you a lot of insight. Each line, each shape you draw on this is going to represent some physical understanding. So please do it multiple times so that you get a strong grasp of the concept. All right. So with that, I would like to stop this video now. In the next lecture, next video, I'll try to solve some problems of CV. And then we'll also discuss how the CV changes with some parameters. Okay. So yeah, I'll see you in the next class, next video. Thank you so much. Have a good day.